All right. So we've already discussed a little bit and sort of gone into some tools that you can use. There's some Python tools that you can use to include with YT. John talked about PYX and how you can install that as like another Python library. And I'm just sort of going to expand on that theme and talk about some ways that you can use YT and Python and expand upon it using other Python libraries and also some techniques outside of Python to sort of just make your data analysis just a little bit easier. So I'm going to have a few example scripts that you can try out. So please go ahead and download them from that Bitbucket repository. Really easy way to do that is to just type this line here, hg clone, and you'll clone the Bitbucket repository in your terminal, and you'll just have the scripts and the talk actually is in that repository as well. Oh, okay. So if you need to just copy that path, you can go to the IRC chat room and just copy it over. And then for the examples we're going to look at, we want to copy or link a data file. You can use any data file you want. Well, I would actually advise you to use the gash sloshing number 150, despite how long the name is. So has everybody got all the information off that slide they need? So just a sort of a brief outline, just very briefly, I'm going to talk in the beginning of like how I see what the advantage of using YT and Python for data analysis is over some of the previous things that I've tried and experienced. Just give you some examples of some Python libraries that I found helpful and others have found helpful that can be interfaced with YT. And then we're going to touch briefly upon the subject of how you can include code that rewrote another language like C, C++, or Fortran, and some of the reasons why you might want to do that. So I say YT and Python together, and I say this for a reason, that when I started using YT about a year ago, or maybe a little over a year ago, it helped me to think about analyzing data in a very different way. I started wondering, how do I do something in Python versus how do I do something in IDL, or how do I write like a script, or not a script, but like a program in C or C++ to do it. It got me thinking about things in an object-oriented way, and we've talked about like lots of objects. We've talked about plot objects. We've talked about plot collection objects. We've talked about objects like spheres and slices and projections, and all the methods and the attributes of these objects. And it's a really helpful way to think about doing analysis. And then one of the other things that just sort of I like to do is when I'm sort of trying to figure things out, I'll open up IYT, IPython, and just sort of test little things out. Test loading parameter files and then trying different things like different things hanging off the hierarchy, or maybe a new thing for the plot collection. And then after that, I'll start writing scripts. So it's handy to have that interactive mode there to just kind of play around and, get a lot of errors, sometimes break stuff. And then once you finally got a sense for what you can do, writing a script after that. So just kind of contrast that to some previous approaches. If you use Flash, and if you've been running Flash simulations for a while, you've probably used the IDL Fiddler tools that come with Flash. It's just a bunch of tools that can read the Flash data really easily, and also you can make some just simple plots and stuff like that. So the pros are is that you've also got that interactive environment to sort of check things out in, and you can write scripts or programs, whatever you want to call them. And the other nice thing about IDL is it's got lots of built-in stuff, right? Math, statistics, image processing. There's a lot of documentation. It reads file formats like HDF5. The cons are, the first thing is the licensing. you got to have a license for HDF5, and if it's not on your machine, you need to be connected to the internet. And what's that? Yeah, sorry. You got to have. Sorry about that. You got to have a license, and if it's not on your machine, you got to be connected to the internet. Or worse yet, if it's behind a VPN like it is right now, for me, you have to be connected to the VPN. So it's a little. That's kind of a pain. It can be a little slow, and although people have parallelized the IDL, it's not very easily parallelized. So one other thing I've done is that I've just taken to writing some of my own stuff in C, C++. The pros are is that you own the source, you can run it whatever you want. You don't have to worry about licensing. You can make use of lots of existing libraries that are out there, like HDF5 or the PyFITS library. It's typically pretty fast. You can parallelize it. But the cons are is that you kind of lose that interactive feel. You don't get to sort of play around with stuff because you have to write like a whole program and then compile it and everything. Unless you're already using a scripting language like Python or Perl. And often, I don't know if you've looked into the APIs for HDF5 or PyFITS very much, but they can be pretty obtuse. There's like a lot of stuff that goes into them, and even simple tasks, you have to spend a lot of time staring at them to figure out what exactly you need to do. But with YT and Python, I think you get sort of the best of some of both approaches. You can write scripts to do quick things, to test things out. You have an interactive mode. There's no licensing. As we saw this earlier today, there's parallelizable. YT already reads, probably most of the data formats in this room that we care about. Has an object-oriented approach. And some of the things I'm going to talk about today are, Python has the advantage of having many libraries for math, analysis, visualization, and YT has an extensive online documentation. There's built-in documentation. You can look at the source, you can get help, but that's also true of a lot of stuff for Python as well. So, kind of the foundation for how all this works and how we can do all this analysis is NumPy, which we've talked about a little bit already today. That's the NumPy website, and NumPy arrays are basically just multi-dimensional array objects, and they've got an extensive repertoire of operations and mathematical functions. So there's some really simple stuff like you can have a NumPy array and you can figure out the maximum or the minimum. You can take an average, you can take a standard deviation, you can do a trapezoidal integral. You can do a lot of interesting operations on that, and you can find out some of those first by importing NumPy, and I'm importing NumPy on this bottom point here, just like it does in YT. NumPy is NA, and then you can do dir NA and look at some of the methods that it looks at under there. You can do dir on a NumPy object, and you can see some of the stuff you can do in that case. So that'd be the first thing I'd say is you should check out all the stuff, the mathematical things you can do with NumPy. But the second thing I want to talk about that's already built into YT that's really helpful is H5PY, so working with HDF5 data sets. So you can create derived fields and new data objects like the spheres and projections and slices and stuff like that. But sometimes you really like to have that data somewhere else. Maybe you have some older program that you'd like to read that data into, or you want to save the data for later and then open it back up at some later point. Some examples of this that I've used is that I've created simulated observations where I had a whole series of projections at different different energies. It's say just over a whole spectrum of X-ray frequency, and so I create spectral cubes and dump them to an HDF5 file, which is then read later by a Chandra simulator. I've created particle trajectories and dumped those out to HDF5 files and then read them in using something else. I've used covering grids in YT to generate uniformly gridded data that I then computed FFTs on. So there's a lot of reasons why you might want to dump data to an HTF5 file and open it up somewhere else. And it's a great solution for saving data. I think that we already kind of know that because Enzo and Flash and other codes are already using it. And H5PY is a pretty easy to use Python implementation of HTF5. And actually writing to HTF5 files is already built into YT in a few places. So the first example I want to show is just taking a radial profile and generating it in YT and then outputting it to an HTF5 file. So, and I probably should have put the file name for the script, but if you download the scripts I've got, then that script should be profile2h5.py. So what this script does is that first it loads the parameter file, it creates a sphere object just centered at the center of the domain. It's got a radius of 500 kiloparsecs, and then it defines a number of arguments that need to be fitted into this bind profile 1D. And I'm realizing I probably should have brought a laser pointer up here with me. So we saw the bind profile 1D function earlier today. Basically, we don't have to go into it a lot right now. This is just an example of how you can dump the profile out to an HTF5 file. But it takes the sphere object. It defines a number of, in this case, which are going to be radial bins. It says the field that's going to be that's going to define these bins is going to be the radius kiloparsec field. So the radius from the center of that sphere in kiloparsec. We've got rmin and rmax of the bins. So the total extent of the bins is going to run from 0 to 400 kiloparsec. And we're just making sure these bins are separated out in linear space. So they're going to have an equal width linearly. So we set log space equal to false. Then I take that my profile object I've created, I add a couple fields, density and temperature, and then I call this second method my profile write out h5, which is going to take this file name, which I'm just calling sloshing radial profile.h5. And the second argument here, the optional argument, is the bin style, which basically says that the radius that's going to be dumped out into the file for each bin is going to be the center radius of the bin. The other options are like the lower radius and the upper radius. So has anybody actually tried out that script and been able to get a HTF5 file dumped out? Okay. So if you use h5 dump, which is a utility that comes with HTF5, and you give it the flag G, which stands for the group, and you want to look at the group radius kiloparsec -1D, what you'll get is basically get some output. First, in this attribute, you're going to get the centers of the radial bins, and then after that, it'll have the first data set, which is the density, which is just like a simple one-dimensional data set of density values, and then after that, at some point, it's going to be the temperature. So there you've got like a simple one-dimensional radial profile. You've got dumped out to an HTF5 file. I could see maybe using the radial profile density and temperature to read into a simulation later, to use those to construct a mass profile. Maybe you want to reconstruct a new galaxy cluster simulation, and you can use these as sort of the input profiles for that. That's one option. Something else you can do with that, and this is more of an example of just one way you can read data back out from HTF5 files, is you can plot it. So without going into an enormous amount of detail, basically what this script does is that it opens up the HTF5 file using h5py file, giving the file name and the access and the way you want to access it, which the R just stands for read only, so you're not going to write over the data. And the F that you set equal to is the file handle object. And then if you want to access things inside the file, you just take the file handle object, and it's a dictionary of the different groups and data sets in the file. So in this case, the radius is in this attributes, so you have .attrs x-axis dash radius kiloparsec. This is going to be a one-dimensional array, so we append this append this array notation here, which just means we're grabbing all of it here, the whole slice of the array. And the dot as type float64 just is basically just going to return a double for us. The temperature is also inside the group radius kill parsec-1d, but it's a data set inside that group. So we're grabbing the radial temperature like that as well. And then after that, you just simply close the file handle by calling f.close. Has anybody got any questions about that? I know there's a lot of notation in there. And then the rest of the lines are just like a matplot, a quick matplotlib, a few lines I wrote just to create a plot. And if you run that script, you should get something that looks like that. Anybody have any issues with that? So this is basically just a way to use YT to write out a bin1D profile and then read it back out later. There's a couple other places. I think you can write a fixed resolution buffer to HDF5. Am I missing anything? I think there's...
Any dimensional profiles or 3D based plots.
Right. Something else that might be useful is that in general, you can write any NumPy array to an HDF5 file. So for example, if I were to generate some covering grids, so I had some like three-dimensional NumPy arrays that represented like the data within some box, and I wanted to write that out to an HDF5 file, I would call h5.py.file, just some file name, and except in this case it would be write access, and then I'd call create dataset and create this dataset dens, and then just give it the name dens. This / just means it's like the top of the file if you think about the HDF5 as a hierarchy. And then data is just going to be equal to the dens object, which in this case is a three-dimensional NumPy array. So I write two of these data sets to the file, close it, then later I can open it using read access, and I can recreate those two three-dimensional arrays by calling density out of the file handle. In this case, you can see that this notation gives me a three-dimensional array, and I'm, just making sure I get like a double precision, that the resulting NumPy array is double precision, and then I close the file again. So there's a lot more things you can do with HDF5. This is just some pretty basic examples of how you can pull data, write data sets in, pull them out. So now I want to move on to talk about some other Python packages besides the ones that come with YT, like NumPy and H5PY. And there's a lot of examples of these things. I'm just going to mention a few of them. I'm going to talk about SciPy, PyFITS, and Sherpa, and then just give an example of how you could use all these things together to get from AMR data to something that you might want to put in a paper. You can find others in a lot of places on the internet. A good place to look is the Python package index, PyPy. There's the URL for it right there. And usually for a lot of these packages, installation is fairly straightforward. If the package is on PyPy, you can just type pip, which comes with your installation of YT, pip install and the package name. So if you want to install PyFITS, you just type pip install PyFITS. We installed PYX that way this morning. Or if you download a tarball, the tarball is going to have something, often will have something like called a setup.py in the top of the directory structure. And so you can install that into your YT Python distribution using pyYT setup.py install. So to just briefly mention a few of these things, SciPy is kind of a counterpart to NumPy. It's basically scientific tools using NumPy arrays. It has a bunch of methods for statistics, optimization, integration. So NumPy has a trapezoidal integration, but there's a few more things in SciPy. You can do linear algebra, FFTs. There's signal and image processing routines, ordinary differential equations, some special functions like Bessel and all that other sort of stuff. I found it a little difficult to install because there's some dependencies that It took me a while to figure out how to get them all met on the server I was installing on, but once you have all this stuff, it can be worth it. So moving on very quickly from that to PyFITS. Is anybody here familiar with FITS? So FITS is it stands for Flexible Image, somebody help me, Transport. And it's a lot of observers use FITS files. You know, so you might get like a FITS file of like Hubble data, or in my case, you get a lot of FITS files of Chandra data. I know my postdoc advisor, Maxime, likes to get simulation data in FITS files, so because he knows how to open them up and mess around with them and have a look at stuff. And so it might be really useful for whatever reason to be able to read and write FITS data. So FITS data comes as like image and table files. What I'm going to talk to you mostly about is images. And what I use PyFITS for is writing slices and projections to FITS files. So you can get PyFITS at this, get some of the documentation at this URL, but you can also type pip install PyFITS. And the nice thing is, and this is, you know, this is a script you can run yourself right now if you have PyFITS installed by pip install PyFITS. But this is just a little simple script that what it does is it takes a parameter file of that sloshing data set. It assumes the z-axis, the slice coordinate is right at the center. There's the center of the domain. And it creates a slice object of density and temperature. And then what we do is that we create a fixed resolution buffer I'm calling image out of that slice object. 600 kiloparsecs width, 1024 cells, and then in YT you can take a fixed resolution buffer and you can call export FITS on it, output a FITS file. And what they'll basically do is they'll just take the fixed resolution buffer and dump it into the FITS file. Now that's really handy. But after I started using it, I found I preferred some more fine-grained control. So what that will do is it'll take the fields that you specify. If you specify all the fields, if you don't specify any fields, it'll just take all the fields in the buffer. It'll dump them to individual FITS files. I wrote a script that takes all the fields, dumps them into one file. It modifies some of the FITS header keywords for inputting like a coordinate system into the FITS file, because programs that read FITS like to be able to find the coordinates. Like DS9, that's one of the programs I'm going to show. The simulation time, you can basically write anything into the FITS header so that the FITS file contains some of the information that you have in your simulation. Like if you want the FITS file to have like the redshift, if you have a cosmological simulation. And so I've included this script that basically does a lot of these things. So feel free to use and modify the write fitsfile.py script to your liking. So I'm just going to take a second to, I already generated one of these files here, so I'm just going to take a second to open up DS9. So DS9 is a program written at CFA that reads FITS data. And this is that sloshing data set. We'll zoom to fit the frame a little bit. And you can, it's the nice thing about it is it's an interactive image viewer. So you can play with the, I'm trying to figure out how to do this without the mouse, but you can, like Maxim likes to play with the color bar. You can like use the mouse to kind of change the way the colors work and that sort of thing. So this is the file that was created by the default YT thing. So that way I just changed the color bar. But the file that has the file that I created using the write fits file .py routine. So I'm just going to open up a second FITS image here. What this does here is that it has actually both of the images in it. And then if you notice up here, sort of look in the upper left-hand corner of DS9, I've got the coordinates set in there. So every FITS file will have the image coordinates in terms of just the pixels, but this FITS file has the physical coordinates in terms of kiloparsec. So that's one of the things that that extra script I wrote does for you. So going back very quickly to the talk, another tool I found pretty helpful is Sherpa. Sherpa is a fitting, plotting, and analysis tool. It was originally developed for analysis of Chandra data. It was included with the Chow tools, which are the tools for analyzing Chandra observations, but now it's mission independent. So basically you can take like an image and you can fit like an image model to it, or you can take a spectrum of some kind and you can fit like a lot of different spectral models to it. You can find it there at that URL right there. I'm not sure if you can get that from pip or not, but it's great for analyzing simulated observations. So if you create like a simulated projection from some kind of mission, whether it's like X-ray or radio emission or something like that, and you can create like a synthetic spectra from like a number of these files taken at different frequencies, then you can just fit that spectra into Sherpa and you can fit it to a model and basically get out a lot of interesting analysis that you can compare to real observations. So basically an example of how this is working in a paper that I've just about finished is that I used YT to read in flash data and make a projection of radio emission. I used SciPy to I used the convolution function in SciPy to smooth the map, like convolving with the Gaussian to mimic the radio beam. PyFITS creates the map, so I've got a map here. This is showing what it looks like in X-ray, so you see like the spiral structure, and this is what's going on in the radio here at 3 different radio frequencies. And then I create spectra from these different radio frequencies, and using Sherpa I'm just fitting power law models to sections of these spectra, and I'm getting spectral indices for the power law spectra at different epochs. So did all this using Python with all these tools installed, and basically just did it all together as one, as basically one workflow. So you guys have probably lots of different other different examples that you could come up with. And the nice thing is that I did all this using Python that came with YT, and I didn't have to have like a whole bunch of stuff that I piecemealed together. So the last thing I want to talk about is just provide a very simple example of is including code from other languages and calling that from Python. So it is a little bit more complicated than just installing Python packages and importing modules and calling the methods and functions from those, but sometimes this is something you might want to do. Code you compile in these other languages is often faster, and you might have code that you don't want to rewrite. This was the case I had. I had a lot of C and C++ routines that I had written for another Flash library, and I had some stuff that I just didn't feel like rewriting, and so I found out that you can actually call functions in C and C++ from Python. So we're going to look at a simple example. The way you do that is this thing called Cython. Cython is basically C, C++ extensions for Python. The structure of the language is very close to Python, but it also supports calling C, C++ functions and declaring C types. And what happens when you create Cython code and you run it, the Cython files get compiled to C code. Then you create some shared object files, and then these shared object files are imported as Python modules when you run a Python script. And there's the Cython website to get some more information. A lot of the heavy-duty stuff in YT is written in Cython, or there are C routines that are written and compiled, and then they're called by Cython, and then the Cython modules are called by Python. So what you need to do is that you need to write a wrapper in Cython that will translate the NumPy arrays, the multidimensional arrays to C arrays. You can pass those arrays to a C routine if you want to call one, and then the Cython code translates the result back to Python code and then hands it back to Python. You have to set up script that will act as sort of a make file for the module. This is done by something called distutils. I know I'm sort of talking about a lot of stuff here, so I think the basic idea here is just to provide you with the basic information and the examples, and then, you know, if this is something that you'd like to do, you can. This provides you sort of a platform to start exploring it in more detail. And then you'd write your Python script to call the module. So our simple example is I'm taking a sphere of 100 kiloparsec radius centered on the simulation domain that data set, and I'm computing the minimum cooling time out of all the cells in that sphere, assuming only free emission, Bremsstrahlung. Now, this is a really bad application for writing your own C code and calling it from Python and calling it from YT. You've already got a much better way to do this in YT. It's much better to create a derived field like tcool and then using the query tools in YT to query at the minimum. But this is just a pretty simple example I thought of. It's just there to, you know, so that we don't have to worry about too much of the ins and outs of what the code does and just focus on, you know, what's being called and how the data is being passed back and forth. So the files that you need for this example are all inside the repository. The first one is a Cython file called cytcoolmin.pyx. It's a Cython file that calls the C routine. This underscore tcoolmin.c is a C routine that performs the calculation. It just loops over all the cells and it figures out what the minimum cooling time is. There's a header file for that C routine that's important also for the Cython file. It provides the definition for the function. There's a setup script that you're gonna run Python on. To basically what it does is that it will take this Cython file, it will compile it to C code, then it will compile that C file with this C file and create a shared object file, and then tcoolmin.py is the driver script. So the first file I want to look at in just some brief detail is the Cython file, this .pyx file. So you can see that at first it's very similar to Python. The syntax looks essentially like Python for the most part. The thing you do at the top is that you import numpy as np, and then these C imports are basically defining C types. So the top thing is importing things as Python types. The next things are importing things as C types. So that when you compile it in the C code, that the compiler is going to be able to things appropriately. The next is that function you're going to call that belongs to the C routine needs to be defined. So I'm defining that from the header file that I mentioned earlier. So this is the function void tcoolmin. So defined as a C type. So in Python we have def for functions. In Cython we're having the cdef, which is basically just defining it in terms of C. So we have to call that function. This is a Python function, and what it's being passed from the Python driver script is some numpy arrays. So these np ind arrays, which have double type and they're one dimension, this indim1. So basically I'm just passing it the straight numpy array from the sphere object, the density, the temperature, and then the position arrays also of the sphere, so that I can not only return the minimum cooling time, but where that minimum cooling time is. So then I'm just defining a few other variables. Again, these are defined as C types, the minimum cooling time, and then the eventual positions that are going to be the location of the minimum cooling time and the number of points in the array that's being passed. And then the next thing that's done is that I got to take the data in these numpy arrays and I got to convert them into C arrays, basically. So I'm defining double pointers here in C to these new variables here. So these are basically just like C arrays. And they're being set equal to the data that's inside each of, they're pointing to, rather, the data that's in each of these NumPy arrays. Then I got to feed this function that I'm going to call the number of points. So I'm calling just the Python routine len on dens, and it's giving me the number of points in dens. And it calls tcoolmin. It passes all this stuff. It's passing this other stuff down here, the tcoolmin and the x and the y and the z by reference. So we define these variables up here. It's passing them in here. This function is going to change them and send them back. And then in the end, it returns these values back to the Python script. This is the C routine that we call. You don't need to worry about too much. It's a pretty standard C routine. There's nothing special in it or different. You can tell I've sort of eliminated a number of lines here, some of the constants that I'm defining here. Don't need to spend a whole lot of time worrying about this. It's just a pretty standard C routine, unless you can find a mistake in my computation of the cooling time. This next thing is setup script, and unfortunately I don't think I have enough time to explain all of the things in this setup script. Basically, this setup script is using the Python utility distutils that basically is kind of like a makefile for creating Python packages, whether it's packages of pure Python or whether it's packages that include Python extensions into C or C++ like this. But basically, you can see it's very similar in at least a form to a makefile in that you have to define like some sources that you want to compile, libraries. So this is like the math library. This will get, used by GCC as -lm when it creates the object file. You can specify some library directories. You can specify include directories. In this case, we have to specify the include directory to get the definitions, the declarations for NumPy arrays, and there's actually a handy function, na.getInclude. It just returns the path of the include files for NumPy in that way. And then we got to import some other stuff. And then basically, what we do is that you create this this list here and this function. That basically what it's going to do is when you run this script, it'll put all this information together, it'll call setup, and it will build your shared object file. There's documentation on the YT page that I'm going to mention in a moment that goes into detail about what all this stuff is. But for now, it'll be just sufficient to run it, and we'll do that in a minute. And what we have here is the actual driver script. So it creates the PF, it creates our sphere object, and then it takes density, temperature, and the positions of the cells in the sphere and dumps them out to NumPy arrays. And then these NumPy arrays get passed into a couple of different functions actually. This calc tcoolmin is actually defined up here in the lines I didn't include because they wouldn't all fit on the slide and be easy to read at the same time. So that's going to return the same information as the module that we're calling from the C shared object file. And the reason we're doing this, I want to illustrate that as long as you obviously have the same algorithm, you're going to get the same answer, but also going to illustrate the time difference it takes to go over this loop in Python versus over this loop in C. So if you have all these files ready from the repository, this is what you have to do to see this example in action. First, you have to run the setup script that will create the shared object file. You do that by running pyyt on setup script tcoolmin setup.py. This build_ext-i basically means that you're going to be building. It's telling it what you're building is a shared object file, an extension away from pure Python. And when you run that script in that directory, what you should get is you should get this file, this shared object file, cytcoolmin.so. So has anybody been able to do that? Okay. Yeah. Okay. Good. And if you have the sloshing file inside the same directory, you can just run pyyt tcoolmin.py, and it should go through and perform all the things in the driver script. And what the output is going to come out as is this. So what it's outputting here is, this is the minimum cooling time in gigayears, 2.044 something. This is the X, Y, and Z in centimeters. So a little odd the way I wrote it there, I guess. But when you call it using the Python function that I defined in the driver, it took about 2.8 seconds. Not a big deal. But when I did the same exact thing calling the Cython module, it took like 4 times, 10 to the minus 3 seconds. So it happened a lot faster. And if you're doing like a bunch of these things, or if you've got something really complicated, it might be a lot better. Or if you've got some code that you already wrote that does this, pretty well, then this is one of the advantages you get. It will often be much faster. So that was a lot of information I just threw at you at the last bit, and so you should probably check out the YT documentation on external codes, which is at this URL here. It's got a bit more of an involved Cython example, and it steps through in more detail all of the things that were in the files that I talked about. You can also look at distutils, which is sort of what is driving the setup script and sort of enabling you to put all this stuff together and to sort of create your own Python package or your own external module for you to call. So I'm just going to throw out a couple other examples of some things that are going on. There's some preliminary, I don't know how well at what stage it's at, but there's some preliminary ways to interact with YT using ParaView. There's some people talking about having visit and ParaView, and and YT interact if that's something you're interested in. We're going to talk some about inline analysis tomorrow. Venkat's talk is going to be about what they're doing in Argonne with inline analysis, and maybe we'll have some interesting collaboration. I know that there's some preliminary stuff using, yeah. Okay, so the inline analysis for YT and Inzo is pretty advanced, so that's good news. So there's just some other things that you can do that's a bit external to just using YT and Python. So for me, like, YT has been sort of not just a great tool set, which it is, but it's been sort of a gateway, I guess you could say, into looking at analysis in a Python way, which I think has been much more productive, and I spent a lot less time figuring out how to get data analyzed and actually just looked at it. And there's lots of external libraries for Python that can do just a lot of different things, just about whatever you might need. And if you got old code in C or C++ or even Fortran, because you can call those Fortran's routines from C routines, you can reuse that and call it from Python in Cython. And if there's any questions or anything else we need to talk about, that's